In this video, we're going to solve logarithmic equations. They're called logarithmic equations because the variable is inside of a logarithm. In this case, it's the natural logarithm, log base e. Now, in order to solve these, what we're going to do is we're going to use our properties of logarithms. We're going to use one of the inverse properties. We are going to use the first of the two inverse properties that we've talked about. And if you're not familiar with these, please check my previous videos where I discuss these in more detail. But we are going to use this first one. Notice it says that if you have the log of some base applied to something, and you put that on an exponent as an exponent on the same base, notice these bases have to match, then what you get is just what's inside of the log. So you can get rid of the log this way. And so this is the property that we're going to apply. Now, if we look at what we have here, on the left-hand side, that would be fine. I could just use that property on the left. But on the right, I have two separate logs. So what I'm going to want to do here first is combine these. So the first step is to combine the logs on each side of the equation. Well, we have another property here, the product property of logarithms. The product property says that if you have the sum of two logs of the same base, notice the bases are the same, that can be written as the log of a product. So that's what we're going to do here. We're going to take the product of x and 5. I'm going to write that as 5x. We usually put the number in front of the variable. And now I have a log on the left and a log on the right, a single log on each side. So now I can apply my inverse property. So what I'm going to do is put the logs as an exponent on the same base that they are logarithms with respect to. Well, natural log is log base e, so I'm going to write each side as an exponent on e. Now, what does the inverse property say? Well, the inverse property says that the exponential function and the logarithm essentially cancel off and just leave me with whatever the exponent was. So these essentially cancel off and just leave me with the x plus 2, and these cancel off and leave me with the 5x. So now I can proceed to solve this equation, subtract x from both sides, divide both sides by 4, simplify, and I see x equals 1/2 is my solution. Now, one important thing you're going to want to do in these problems involving logarithms is check your answers. Sometimes you may get something down here which is not a solution to the original problem. We call that an extraneous solution. So such a solution you would want to rule out. If we plug this in up here, you'll see here on the left-hand side we have log of 1/2 plus 2. Well, that's 5/2. Over here, we have log of 1/2 plus log of 5. Well, remember that the property of logarithms says that we can combine these and write it as log of 5 times 1/2, and that is log of 5/2. So the left-hand side and the right-hand side do match. Everything's fine, and so this really is a solution. Our next logarithmic equation is this one. Now remember what we did in the last one. We combined these logs so we had a single log on each side of the equation. Now I could combine these two using one of our properties. We have a quotient property. The difference of two logs becomes the log of the quotient, and I could use that property over here. But I think it would be nicer if I actually added log 2 to both sides. And now I have a plus, and so I can use the product property instead. The sum of two logs is the log of the product. And I'll write 2x instead of x times 2, as we customarily do. Now, as we did in the previous problem, we will put each log as an exponent on e. And again, we're choosing e because it matches the base of the logarithm, so that's going to make this work out the nicest. The e and the natural log cancel off, and so I'm left with x minus 3. The e and the natural log cancel off, so I'm left with 2x. Okay, well, we'll subtract x from both sides. And I see I'm getting x equals -3 as an answer. Now, before I box this in, I'm going to check this solution. We need to make sure that this works in the original equation. Well, if I look over here, -3 minus 3 is -6. I'm taking the natural log of -6. That right there should jump out at you. Something's wrong. We can't take the natural log of a negative number. Can't take any logarithm of a negative number. That is undefined. And so this, in fact, While it is a solution to the equation that we came up with here, it is not a solution to the original problem. It's what we call an extraneous solution. And so for this problem, the answer is no solutions. Okay, here's our final logarithmic equation to solve. Well, I think what I'll do is I'll proceed like we did in the last problem and get rid of these minuses. I'm going to add log base 3 of 5 to both sides, and I'm going to add log base 3 of 7 minus x to both sides. This is what we get. Well, now we can go ahead and use our product property of logarithms, which says the sum of logs gives us the log of the product. So let's go ahead and use that on both sides. The sum of these two logs is going to be the log of the product. And we'll use it on the right-hand side. The sum of these two logs is going to be the log of the product. Well, 2 times 5 is 10. Now what we can use is the inverse property. We know that if we want to kill the log, we can just raise the log as an exponent on the same base. So what's the base of the log? It's 3. So I'm going to write each side as an exponent on 3. Well, the inverse property says that these cancel each other off, and so I'm left with this equation. Well, this is a polynomial equation. We know how to solve these. It would be a good exercise for you right now to pause the video, solve this polynomial equation, and see what you get. We'll compare our answers together. Okay, so the work would be as follows. We get 28 minus 11x plus x squared equals 10. I think I'm going to rearrange terms with the highest degree term on the left, the x squared, minus 11x. I'm also going to subtract 10 from both sides. We always want to do that. We always want to, when we solve a polynomial equation, we always want the right-hand side to be 0. Because that way, when we factor the left-hand side, we can get solutions that way. So we're looking for two factors of 18 that add to negative 11. Well, I know what those are, negative 2 and negative 9. So I see I'm getting two solutions here, right? Because when we have a factored expression equal to 0, we know one of those two factors must be equal to 0. That's the only way I can get 0 as an answer here. So either x minus 2 is 0, in which case x equals 2, or x minus 9 is 0, in which case x equals 9. So here are my two solutions. Now, I need to check these to see if either of these may be extraneous. So let's check the 2. If I go up to the top here, if I plug 2 in for x, I get log base 3 of 2, 4 minus 2 is 2, minus log base 3 of 5. And on the right, we get the same thing. Log base 3 of 2 minus log base 3 of 5. They are equal. This is part of my solution. Now let's check the x equals 9. We'll see if that's part of our solution. If I plug in 9 for x, 4 minus 9 is negative 5. Whoa, right? That's a negative number. Can't take log of a negative number. This isn't defined, and so it can't be part of the solution. So this is an extraneous solution. So our full solution is simply x equals 2.